What's up, people? I want to talk you through the two options that you have to figure out how much torque a force makes when there's some angle stuff going on. What we have said so far is we have said that torque, by definition, is product of R and F. But there's more to it than that. All right, because everything that we've looked at so far involves situations in which vector R and vector F have been perpendicular to each other. Whether or not you know it, we've looked at cases like this. We got a plank. Here's a rotational axis sort of thing. We got an mg there. We got a tension here. We've got R vectors like that. And we've had right angle situations every time. And as you might be able to imagine, when a vector R and a vector F are perpendicular to each other, well, a force creates as much torque as it can create. But this force still creates some torque. If you think about torque as the tendency of a force to make an object accelerate angularly about an axis, sure, even if we pull this way, that still has some tendency to make this system rotate about that axis like that. Wouldn't you say? I would. So let's talk a little bit more specifically about how to handle situations like this. Well, one thing you have to do is, or what you should really get comfortable with, is drawing yourself R vectors like we've talked about. So here's a vector R, again, that goes from rotational axis to point of application of force F. All right. Now, well, the situation here is that the entire force F does not create torque. Right? There are two components of F. There is this component that I'll call F parallel. Oops, not long enough. That long? Longer. F parallel. And what I mean is parallel to R. And then there's this component of F perpendicular to R. And that's the component of the force that creates torque. And only that component. Okay, so if we look at this angle here, this angle between vector R and F, let's call it well, we can sort of say it's that angle there between those two vectors. Well, it means it's also this angle here. Well, F perp is F sine theta. Okay, so if we really want to express how much torque force F creates, one option that we have, so I'm sort of putting this in quotes, but what we really can do, option one, is we can say that the torque generated is R times F perp. And this is the component of force F perpendicular to vector R. Okay, so that idea is super important. So look at this F parallel, right? The thing about pulling this way, that has no tendency at all to create, that angular acceleration about that axis. Only this perpendicular component does. Okay? So to express the size of the torque in this case, we would say it's R F sine theta, because F sine theta is how big F perp is. Sound good? Good. Now option two, same situation. We still have this vector R. Come on, still have vector R. Well, here's what you can do in situations if you feel like it. What you can do is we can do what's called extend the line of action of force F. This is called the line of action of force F. So this is, we'll just label that. It's called the line of action of force F. you get it. Come on, would you? Of force F. But what we can do now is we can draw a component of R that's perpendicular to that. And perpendicular, yeah, it's pretty darn good. So this is called R perp. It's the component of vector R that's perpendicular to force F. And so what this is saying is, well, this whole force, it's like this whole force is, ooh, can I do it? Hang on. It's like this whole force is acting right there. All right, so it's like, here's what we're saying. Watch this out. Uh-oh, wait, copy over here, paste. Yeah, good. So the way this thing is set up with F acting here at that distance R, it's the same amount of torque as if the whole force F acted at this perpendicular R. Okay? And so let's take that same angle we defined before. Here it is, here it is. Well, in this case, R perp is R sine theta, right? Opposite the angle. And so if we say, well, our option here is to say R perp times F, we get that the torque is R sine theta times F, which you can write as RF sine theta, just like we did here. Just like we did here. Those are equivalent. Okay, so what we're trying to get at is you really have two options for when we say torque is, quote, the product of R and F. That's not enough. It's not necessarily true. What is true is that torque is the product of R times the component of F perpendicular to R, and or it's equal to the component of R perpendicular to F, or the size of the component of R perpendicular and F product. And those are the same thing. We've showed you that in both cases you get the same answer. So maybe you're saying, well, then how do I know which one to do? Well, I'm going to show you a couple different situations in which one of the cases is the appropriate, one of the options is the more appropriate thing to do, in my opinion. Okay, so here's a wire. It's this, used to hold up a plank. This is like a pole or something like that. I don't know, right? Fair enough. And we're asking what torque the wire's tension produces about this axis located at the wall. Okay, well, here's the tension force. Here's vector R. And in this case, that's funny. Never mind. In this case, for me, it's easier to identify T perpendicular. I hope you can't hear my kids, boy. Easier to identify T perp than it is to do R perp. For me, it is. All right. And if this angle is that 30-degree angle, then, well, that's the same angle as this angle, and then T perp is opposite that angle. So this torque created by the tension force, what I would do in this case is R times F perp. Now, what I haven't done is told you the length of the plank. Oh boy. So that's, well, whatever the length of the plank is times T sine theta. I haven't told you anything. I mean, there's a way to answer this question. It's a different, there's more to it than this. You would have to it's a different solution to find the, what T is. But that's how you would express the torque. Okay? Sine 30, sure. Now in this case, here's a different one. In this case, here's a ladder leaning up against the wall. And we're looking for how much torque the ladder's weight creates about this axis. All right, well, look, here is force mg acting on the ladder. Here is R to mg. And in this case, for me, it's easier to break up R into components. So here is a component of R perpendicular to mg. Notice what I did here is I extended the line of action of mg. It's a pretty good thing to be able, pretty good skill to be able to have when you're trying to do torque analysis stuff. So in this case, what I would do is I would say the torque created by mg is R perp times, well, mg. And this R perp, let's see, we haven't said where an angle is, but if, let's say, this angle was defined here, well, notice that R perp happens to be adjacent to that angle, so I would now say this is R cos theta times mg. You get that? We got R like this, there's the component we're looking for, there's the angle, that's adjacent to the angle, so that uses cosine. Okay? And just so we're sure, like, or just so, the vector R, well, that's still this whole thing. That would be the half the ladder's length. That's how long this vector is, times cosine. And we could change the order, perhaps. Maybe it's most common to do the cos theta. Well, I'll just leave it like this. L over 2 cos theta times mg. Okay? So how do how do I know, right? In this case, I broke F into components. In this case, I broke R into components. How do you know which one to do? Well, for me, look, T's off axis, and what I mean by off axis, like here are standard axes, right? So in this case, F is off axis. So therefore, break F into components. Notice in this case that it's R that's off axis. So, break R into components. That's my approach. And there isn't a right answer. I mean, you can do this one by leaving R alone and breaking mg into components, but in my mind it's more difficult. Okay? So you're going to see some situations in which you have choices. I mean, quite literally, there's practice problems that look very much like these, where you have to figure out which thing should I break into components. And what I would do is ask yourself, which vector is off axis? Is it R or is it F? Whichever one's off axis, I would break it into components. But we need to know and be able to use the fact that, well, this is sort of true, but this is more absolutely true. That this is how much torque a force creates. It depends on a component of one thing perpendicular to another. Okay? Okay, buddies. Thanks a bunch.